So this work is based on formulation of a general framework by Robert Oakley. And this is a joint work with him. So first I will just make some comments on the motivation for this study, which is the measurement problem in quantum theory, in the sense that we don't have yet completely developed formalism to describe general operations in quantum field theory. I will mention what is the abstract positive formalism and how from this abstract framework we can find several known theories and also find other and their generalizations. So we will discuss a bit more what is the convex operational framework when we have time direction. Then this framework, convex operational framework in space, and we have a space-time notion, and this is what is called the positive formulation. And then I will mention how we can compose measurements in this framework. So, why the problem of measurement theory is hard in quantum field theory? One point is that there is a problem on having well-defined measurements when we have when we have sequential measurements, the violation, there is a chance that we have a violation of causality. This is what Doreen also was discussing as a motivation. She mentioned the Sorkin's impossible measurement. So there's no joint probability distributions for sequential measurements. Another problem is that the correlation functions that we usually take as the main objects of quantum field theory are products of fields at different points, so they're not local. Moreover, they are mostly defined and considered as vacuum expectation values. So the initial and final state is usually considered to be the vacuum state, which first is not general, but if we try to generalize to other states, these objects are complex and they don't correspond actually to expectation values. So there is a need to construct, to have a positive and real map so that we can encode the measurement process in quantum field theory. And this is not obvious to construct, to do. Okay, so here is a sketch of this abstract positive formalism, which in the middle I have this picture of boxes and links, and from this, okay, everything is connected, but if in one direction, if we add the time direction and the normalization condition, we can have frameworks such as the generalized probabilistic theories. But more specifically, if we add the quantization process, if we do the quantization process, we can get the non-relativistic quantum theory. So here is this is depicted in this diagram. There is a time direction. The boxes are operations. they are progressing time, and here we have a final state, which is a state of the maximal uncertainty. So we have done the experiment and we have discarded the result. On the other side, I have in this framework, I have added locality and space-time. So the notion of locality in this formalism is the classical notion of locality, in the sense that you can have interactions only in the closest, through the closest regions, nearest, the nearest neighbor approximation. And space-time means that we have local space-time regions, which are abstract, abstract in the sense that they're general. They don't necessarily have to be like that they are that they have space. There is some foliation. So from there, we can have the framework of field theories. And by this, I mean both classical and quantum theories, depending on what kind of process you do. So I have separated here more these theories, and I have written here pure and mixed, I mean formalisms, in the sense that here we are having the statistical field theory, and here the classical mechanics. While in here we have then pure state, the closed system, quantum mechanics, while here we have the generalized, it's a more general framework that accommodates mixed states and POVMs. Okay, so what makes, okay, let me comment that what makes a big difference on what kind of theory you have is that the state space that you have in its case. So, as an example, and I will mention it later, here you have the operators defined on Hilbert space, while here the generalized operations are defined on the space of operators of bounded operators on the Hilbert space. Okay. And so here I have a table of the main objects of this framework. So space-time region, so the main objects are a space-time region with a hypersurface that is the boundary. And on this region, we define the space of solutions in this. So equivalently, we do the same on the hypersurface. And in this region, we define probes, which are, with this, we can encode several operations on the system, meaning either preparation, measurement, or even time evolution. And this defines a space of probes. So the influence of the rest of the world in this space-time region is encoded through the boundary conditions, which are again defined in space of boundary conditions. And to have predictions in the theory, we need a probability and expectation value. So these are defined here. Well, here are these are objects which are in its theory, they represent the inner product of the theory. And the expectation value is defined in a similar way, as a sum over the different kinds of probes. So as I said, the operations can be either unitary evolution or evolution under the influence of some probe. And these define respectively probability maps and probe maps, or observable maps. Usually, unitary evolution is defined as a null probe, while primitive probes are the ones that belong to the positive cone of this. It is a subspace of the space of probes. There are well-defined operations of composition of regions, which result in composition of probes, and then decomposition of hypersurfaces, which consequently can lead to decomposition of the state space. Okay, let's make it more precise. So, for example, if we have here this setup, so we have an initial and final time. Here are the initial and final boundary conditions, and these actually are the states defined on a Hilbert space for quantum field. Here is an operation which I have denoted as P, rho, and the idea is that this is the space that there are selective measurements which are defined by projection operators, and non-selective measurements which can be defined as they are convex combinations of these projective operators. The probability is defined in this way. This is some kind of pairing on this is on the space of probes together with a boundary condition by on this. So it's a function on the space of probes and boundary conditions, and gives a real value. And respectively, the expectation values are defined in this way. So it is important that here the probes are the space of states and of probes are partially ordered vector spaces. And this, because this makes this framework convex operational, exactly because you can write this kind of you can decompose, you can write probes as sum over projection operators. And here is a comparison of quantum the state spaces and the operations on quantum mechanics and or quantum statistical mechanics. So in this case, the state space is a Hilbert space. The operations is the unitary time evolution. All these are maps from the Hilbert space to another Hilbert space, or the same. Probabilities are defined through this inner product and correspondingly the expectation values. while in more generalized quantum theory, the state space is the space of the self-adjoint operators on Hilbert space. The elements of the positive cone are the pure states. We have an identity operator on B. We have as well there. But here is the state of maximal uncertainty. There is the inner product is the Hilbert-Smith on the space of self-adjoint operators, and there is a condition of normalization that I have not here. So quantum operations are completely positive maps and can be decomposed in this way, where Ki are Krauss operators. The time evolution superoperator is the map correspondingly in the real operators. And then the state is evolves by left-up. There is a transition amplitude, and the composition, you can compose transition amplitudes in different times. So if you have a time interval, you can write it such that you can write the transition amplitude in the whole region as a sum over subregions in this. Here, Xk are vectors on the Hilbert space, on the boundaries, on the surfaces that of these regions that that decomposes the more general region. And the observables, again, they are again functions on the space of bounded operators. And here is how they evolve correspondingly. So there are Krauss operators that act on this. Okay, so how we do quantum field theory in global hyperbolic spacetimes. So we have here a region that here sigma 1 and sigma 2 are two regions, but those hypersurfaces that foliate the space and time. So we can consider that this is the setting that of Minkowski spacetime of quantum field theory, or in more general global hyperbolic spacetimes. So this region can be decomposed as the time interval times the rest of the space, and the boundary is given as a union of this with this surface. So here I have this bar because these surfaces are oriented, and this plays a role in on what on the state spaces and the objects that we are taking on this. So there are some. For example, here we're taking this the complex, the conjugate Hilbert space. So in here, in the let's say, yeah, okay. So that's the reason. So usually these Hilbert spaces on these two hypersurfaces are considered to be the same because of the time translation. And we can define a transition map in operator formalism or with the path integral. And the probability is given as the square of this transition, the transition map. We know that, note that there is a normalization condition here. So this is this probability is well defined. I will come to it. And correspondingly, we have an observable map, which is I have noted here as F. Consider it as an observable that acts in the region. It's like a probe. So we can have a general operation. So this, for example, in the setting of the usual setting of the asymmetric matrix, if we push the hypersurfaces at t minus infinity plus infinity, we're having this setting. So in the picture, I have written V as U as the time evolution, but we can have interactions. So F represents the interaction that we can have in this region. So here I'm using, let's note that I'm using the path integral because I want to generalize this picture, and it's more natural to do this in this way. So that's what I will do in this. So from this picture, I would like to pass to this one. So in this, I have a region, but there's no time for space direction. So it's a general metric, let's say, if there is a system. So there is a boundary on which so from this picture can be, you can see that this and this can be written as a product of space, of the Hilbert spaces. And I can generalize this to this picture. So here on the boundary, I can define a Hilbert space on which there is no clear separation of initial and final state. So this has some implementations, such as there is no time setting, so there is there is no initial and final state. There is no notion of preparation, or so the probability correspondingly is defined as what I ask over what I know. So A here represents a subset of the Hilbert space, which represents the states of my question. And S is the subspace of this Hilbert space that actually corresponds to what I know about this experiment. So usually, since there's no time direction, we have a normalization condition. The probability has correspondingly to be generalized. So in the usual cases, in the non-relativistic theory, or in the picture I was showing you before, the denominator is 1, and we usually ignore it. So that will not be the case in a more general setting. So yes, so here, this is the generalization of the amplitude. So this integral is taken over the configuration space in the region. These are the states on the boundary. So they belong from the space of solutions on the boundary. Okay, let me note something which is important. In the previous picture, so when we have space-like hypersurfaces we have well-defined a well-defined initial value problem. There is one-to-one mapping between the space of solutions in the region with the space of solutions on the boundary. And this is the, so there is, that's why if you have a space like a surface, you know already your solutions. Again, this is not the case, but there is a map of the space of solutions in the region on the space of solutions on the hypersurface, and it is a subspace. This is the space of solution, the mapping of the space of solutions in the region on the boundary is a subspace of the space of solutions on the boundary. So I'm noting this. This is the map. So this is a map from the space of solutions in the region. And here also is the space of solutions, the map, the subspace that the mapping that we get from the space of solutions on the boundary. And this is, that's the relation of saying that holds. Okay. So what is important in this amplitude probability maps that everything here? So here, so as I said, here is this generalization. The amplitude map corresponds to the time, the evolution, a generalized evolution in this region. And the probability map, which is defined like that, the sum is over these vectors which belong to the hyperspace on the boundary. So this is what we actually want. We want it is a real positive map, and this probability in this case is well defined. On the other hand, we have this observable map, which generalizes any kind of probes in the region or interactions. So in QFT, as I said, you can consider any kind of interactions like in linear QFT or like perturbation theory. So this is the this is what this observable map corresponds. And we have here the expectation map, which is not actually a positive and real function. It's not a function of the real and positive numbers. And that's what we would like to construct. Also, also its composition. Yeah. So let me mention a bit more about this composition property because it's important. So it's actually based on the notion of composition of the path integral. And this is how you can decompose this. Okay, so the moral here is that if you have a transition amplitude in larger region, in a region M and N, where this is their joint union, then this is equal to the sum overall over the amplitude of in one subspace in N times the transition amplitude in N. And this is how we can write in again this product. Okay, what the way that we would like to construct this is by taking advantage. So let me go back and show that mention that here I have a product of transition of the amplitude map with the observable map. But here, the idea is to take advantage of this of the following. So this is a formalism or that is known as in or spin capital formula. The idea is that you have an initial time, you evolve your system up until some time, and then you go back. So that's what these paths represent. So instead of having time ordered correlation functions, you have path ordered correlation functions. Also, okay, so you can have different initial and final states. So here I have with these kxi1 and kxi2, I denote coherent states. And F is my observable. You can consider it as a source. So in the first path, I have a source, the source F arrow up. And when I go back in time, I have the F down arrow source. Here is a time, an intermediate time, but on which I sum overall the states. So this formalism is convenient. Okay, at the end, I have to take the sources and the initial and final state, right? So that I have well-defined my objects. Yes, so that's the idea. And the advantage is that you can define expectation values, which are actually, well, the initial and final time are the same because it returns to the same state. So you don't have problems as in what is called the in-out formalism in standard QFT, that the initial and final value, the vacuum, are not necessarily the same, and you have to make assumptions to consider them that they are the same. So you have to go to the adiabatic view. Okay. So instead of defining my expectation map, which more generally now I can call them probe maps, we're considering to define this in this way. So if we have a quadratic observable, we can, let's say, split it and calculate it and make this calculation. Okay, let me say a few more about these observables. So this is what is called very observable because of this form. D is actually what an observable that you have a source that you have in your action. So when you have usually where you have the free action, and you can modify it to have interactions. So this is what D represents. So it's the modified action, the source of the modified action, and it satisfies the inhomogeneous equation of motion. So I have written here a result that this probe map of if you take this initial in this format, if you do this calculation, turns out to be this term. Okay, these are. I'm not going to explain. They are related to the. So these psi plus minus are related to the choice of my vacuum and how I have and the positive and negative solution space. So this observability depends on this choice. But it is also important that we have a divergence step. Okay, so this is actually it's a Whiteman function, but if you it is the negative Whiteman function because here we have taken this one is defined on the first path and the other one on the second. The first path is usually earlier in time, and in the way that we have taken this, it turns out to be the negative Whiteman function. So this divergent term appears because we have at the final state we have a discarded state. While if we had a post-selection, we wouldn't have this, and we would get the classical result. So it's important that when we combine, when we want to start combining these probes, to make sure that they